Hi everyone, I'm super excited about this week. So, sun is shining, the weather is nice outside, spring is finally here, and I am back with 2 lecture recordings. So last lectures we talked about tricks for training neural networks more efficiently. So that also includes getting a better predictive performance, building models with a good generalization performance. And one of the tricks was dropout, which helped us to reduce the degree of overfitting. Another trick was batch norm, which normalizes the inputs to each hidden layer, and that also helps us training more efficiently and getting models with a better performance. And finally, we talked about weight initialization, which includes topics like Hamming initialization and Xavier-Glorot initialization, which add a certain scaling factor to the initial starting weights, which also help the optimization algorithms. So today we will talk about optimization algorithms themselves, and in particular we will focus on stochastic gradient descent. That's our usual algorithm in the context of deep learning for performing the backpropagation. So we talked about stochastic gradient descent many times in this course already, and today we will make some modifications to it, adding a momentum term or using an adaptive learning rate. So that will also help with the network to learn faster. So I'm also super excited about Thursday, because on Thursday, hopefully that means I finished up this lecture, I will talk about convolutional neural networks, and convolutional neural networks are a new architecture, or at least a new architecture in this course. And many of you will be using convolutional networks in the final project, because these allow us to do interesting tasks such as image recognition, image classification, object detection, object segmentation, and all the fun things you can do with photos and videos. So finally will be also something exciting, like something new, not just tricks. And then also at the end of this lecture, I will be back with the stuff in the news section, which I think was always fun, where I briefly talked about cool things in the realm of artificial intelligence, deep neural networks, and machine learning. So last lectures I was already struggling with getting the recording done in time, but I think it might be more fun just to add the section at the end this time. So if you don't want to watch it, you can just skip it. But yeah, in any way, to not waste too much time on this introduction again, let me get started with a real lecture recording now. Okay, let's talk about common optimization algorithms. So in lecture 11, the reason why I call this topic common optimization algorithms is because there are many different types of optimization algorithms. And especially also in deep learning, there are many different types currently being used, like little tweaks. And I will only talk about the most common ones, the maybe most useful ones in deep learning. And all of them are based on stochastic gradient descent. So in that way, you can also think of everything we talk about today as improvements to stochastic gradient descent, which help us learn deep neural networks more efficiently. So the slides for today's lecture are again on GitHub, like always. So maybe it's useful if you download them before the lecture, so you can take notes on the slides. Before we get started with the optimization algorithms, just a brief overview of where we are in this course. So we have already covered a lot of topics here, parts 1 to 3. We are almost finished with part 3. So next lecture we can talk about architectures such as convolutional neural networks and recurrent neural networks. So they are convolutional networks are mostly for nowadays videos, but mostly images, and recurrent neural networks are mostly for text and also time series analysis. So many people also apply them, for example, for stock market predictions and other tasks. So there will actually be some students in this class for the final project presenting on stock market analysis with recurrent neural networks. So once we covered these topics, we will also talk about deep generative networks, which are models that generate new data. So models that help us generating new data. Okay, so just briefly to recap, last lecture we talked about tricks. So input normalization and weight initialization that help us learn more efficiently. Today we will talk about more tricks, but these tricks are for the optimization algorithms. For example, we can decay the learning rate that the optimization algorithm uses. We can add a momentum term, or we can also use adaptive learning rates that adapt to the task, or we can use a combination of all of them. So it's also possible to combine all of them. Okay, I added some note to myself here. So also wanted to mention all of these tricks we will talk about today are based on stochastic gradient descent, like I said in the beginning. So they are modifications of stochastic gradient descent, and they are all still first order optimization algorithms. There are some second order optimization algorithms. You probably heard about them in other courses, especially if you took the course in computer science on optimization theory. So, but these are very, I would say, tricky in deep learning because they are very expensive, and in practice there's only a little benefit from using second order optimization methods. So as of today, second order optimization is not very popular in deep learning, and that is why we still mostly focus on first order stochastic gradient descent methods, for example, stochastic gradient descent. And maybe in a few years it will be different. Maybe in a few years there are efficient or promising second order methods out there for deep learning. But yeah, until now we have our first order optimization algorithms, which are pretty robust in deep learning and commonly used, and not too expensive most of all. So yeah, before I talk more about the optimization algorithm though, let me just briefly recap homework 3. So I'm actually not recapping homework 3 exactly, but I wanted to apply some of the tricks we recently focused on last lecture to homework 3 to see them in action basically. And then we will talk about the optimization. So first let's focus on this part, and then later we will focus on the second half. But I will try to keep this short now. So recall in homework 3 I gave you a multi-layer perceptron, and I gave you the whole notebook with different hyperparameters, and I gave you the task to optimize or to find good settings for the hyperparameters that you get a good validation accuracy and test accuracy. So here I'm just showing you an example network. So this network has 3 hidden layers. I'll call them linear 1, linear 2, and linear 3, and 1 output layer. And here I'm just using the 10H activation function, and that's about it. So the first hidden layer has 75 units, the second hidden layer has 50 units, and the third hidden layer has just 25 units. So this is just a relatively arbitrary architecture. It's not the best one that you can use for that task. So it's just one example. So for this example, what I did is, so what I showed you before, I used a random uniform distribution to sample the initial weights. So this is uniform weight initialization. And at the top, I'm showing you the cross entropy during training. So from the first epoch to the last epoch. And you can see that the training and validation loss, they go down, so over time. So it doesn't really matter that one is higher than the other, you can just ignore that. Just what we can see here is that they go down, and it looks like the training converged. So that is pretty cool. However, what we can also see is, actually what we can see is that we can't see anything. So here I'm plotting on the bottom, I'm plotting the accuracy for the training and validation set. And I clipped the plot at 80% because that made the comparison that I have in the following slides a little bit easier. So here the curves don't even appear on this plot because the test accuracy is pretty low, 11.7%. Also the training and validation accuracies are too low to reach this 80% threshold. And remember, we had 10 classes and they were evenly distributed. So that was this fashion MNIST data set. So we had 10 classes. They were uniformly distributed. So even just randomly predicting a class would give me about 10% accuracy, right? So this is really not a good model. So how can we improve that? Or what can we do based on what we've learned in the last lectures to get the network to train better? And also I should say, I played around with the learning rate a little bit and it did not help. It's likely due that because it's a relatively deep network for a multi-layer perceptron. For multi-layer perceptrons, 3 hidden layers is already quite a lot. So it's likely that the initial weights are so bad that it can't even learn anything because of the vanishing gradient maybe, or exploding gradient. Okay, so then here again, this is what I showed you on the previous slide. And then what I did is instead of using a uniform distribution, I chose a normal distribution for initializing the starting weights. This is a small improvement, or actually a pretty significant improvement from 11 to 66%, but still it's not great, so I'm not really happy with that one. So what I did then is I didn't do my own weight initialization, I just used the weight initialization that PyTorch uses. So here in this notebook, I was just using what PyTorch uses, and as you can see, the training improved by a lot. So now we actually see some accuracy values here in this plot. So the training accuracy goes up and the validation accuracy goes also up, and then it plateaus at some point. It's a little bit noisy, but yeah, it's what it is. The test accuracy is 87.88%, so it's much better than this one again. It's actually pretty good. And recall for what PyTorch does by default is it uses the initialization that is quite similar to the Xavier Glorot initialization, which is again more optimal for 10H compared to just a random uniform or random normal weight initialization. So that's good. So what I did then is I used the ReLU function. So I replaced 10H with ReLU. So the performance is about the same. So it's actually lower. It's 0.6% lower. Sometimes ReLU is good, sometimes not so good. But also I should say here we are using again the Xavier Glorot initialization scheme. So that is better for 10H usually. So what I did then is I replaced this the Glorot initialization by the Kaiming He initialization we talked about last time. You can see this is a small improvement here, so it's not bad. I would say it's maybe hard to see, but this is maybe it's relatively horizontal, but it's maybe rather going more up rather than this one is maybe going more down. So maybe more epochs would also get the same performance as this one. Okay, so next what I did is I added batch norm. So last time we talked about batch norm, and it would be interesting to see how that performs. We can see this is again a pretty big jump. I mean, the jump looks small to be honest, but if you think about it, if you have 50,000 classes, and 50,000 is pretty small for deep learning, but let's say we have these 50,000 data points in a data set, in the training set. So improving by 1% on a 50,000 example data set is actually pretty substantial. So if you have 50,000 times 0.01, this should be 500, right? So if you have just a 1% improvement, you already make 500 more predictions that are correct if you have 50,000 data points. And in practice, I mean, in deep learning, let's say we have data sets that are huge. There are like 5 million examples. So in that case, for 5 million examples, you would get 50,000 data points more correct if you have only 1% improvement. And now think about Google, who has like billions of customers who use their search engine every day. And if you have a billion customers and you are just 1% more correct in getting a good search result, then this is actually a pretty substantial improvement. Okay, so that's not where it ends. I have some more to show you here. So here I added also to the batch norm Kaiming He initialization. It didn't make much of a difference because maybe batch norm already helps a lot with everything. So here maybe choosing a weight initialization scheme is not so crucial anymore if we already have batch norm. Next, so what I saw here, of course, you hopefully also saw that there's a lot of overfitting going on. Next, I thought, what happens if I use dropout to reduce that overfitting? So it seems like it's a little bit hard to see because I use the same clipping for the y-axis, but you can see maybe that the training and validation accuracy are very close to each other. So if you look closely, the orange and blue line are overlapping almost perfectly. So that tells me that the network is not overfitting anymore, but I added maybe too much regularization. If I recall, I added 50% dropout to each hidden layer. Was maybe a little bit too much because, okay, now I don't have overfitting, but the performance went 10% down, right? So that's also not great. So what I thought then, okay, what happens if I make the dropout a little bit weaker, reduce the dropout probability maybe by from 50 to 20%. I forgot the exact number, but you can double check. So I have all the code here if you want to double check. So what I can see now is there is, again, some overfitting, but again, the performance is back to, I would say, normal. It's at 87% here. So this is without batch norm. So this is almost like what I had before, but with less overfitting. And then I thought, okay, if I have reduced my overfitting here, batch norm makes things better. So what happens if I combine dropout and batch norm? So that's what I did here. So here in this one, I have batch norm and dropout, and you can see the performance is now 89%. And you can also see, maybe it's hard to say, but it looks like this one goes rather up a little bit. So if I would train it longer, let's say for 100 epochs, I would maybe get more than 90% performance. So for the homework, I asked you not to use batch norm because we haven't covered it back then when the homework was announced. But also, even without using batch norm and without using these weight initialization schemes, you can get a pretty good performance. So one student got almost 91% performance. The student is also the winner of this homework, because I said the winner, the student with the highest performance, will get a small reward, a small book, or rather a big book. But yeah, since we don't have any class sessions in person anymore, I will have to mail the book physically. But I will make an announcement on the mailing list, so to announce the winner and also to arrange the book shipping. So, but okay, this was just a brief recap of homework 3. Not exactly homework 3, but just applying some of the recent tricks to homework 3. So what we learn about today will be optimization algorithms, and I also encourage you maybe to go back to this code, homework 3 code, and apply the optimization tricks we learn about today to this homework to see if you get maybe even better results. Okay. So the simplest way for modifying stochastic gradient descent is learning rate decay, where we shrink the learning rate over time. So before we get to that, just let's briefly recap mini-batch learning. So mini-batch learning is a form of stochastic gradient descent. It depends a little bit on how we draw the mini-batches. So there are many different ways we can do that. So if this is my training set, what we usually do is we divide the training set into multiple mini batches, and then we draw one mini batch at a time, and after each epoch we shuffle the training set. There are different types of drawing mini batches. You, for example, can also randomly draw a mini batch without shuffling and without replacement or with replacement. If you draw samples randomly with replacement, that would be more truly stochastic, because then each sample is independent of each other. So in practice, what's commonly done is not completely, I would say, stochastic, because there's a dependence on each sample or each training example, because we usually sample without replacement. But it does not matter here, really. So what I'm just trying to say here, mini-batch learning is a form of stochastic gradient descent, so it's noisier than the normal gradient descent, what we called batch gradient descent. Again, we use the classic term batch gradient descent, which means there is no stochasticity, so we learn based on the whole training set. We don't have these mini batches. So if we use batch gradient descent, so we would make, in this case, steps perpendicular to these contour lines. Again, I don't want to explain this every time, but this is like our surface plot of the loss function. Oh, what happened here? I don't know. So of the loss function, and we want to reach this global minimum here. And again, this is a very simple cost surface. It's convex, which is something we don't have if we train deep neural networks. In any case, what we have when we have stochastic gradient descent is something that is a little bit more noisy. So here we don't make steps directly leading to the cost minimum, we oscillate a little bit. And also it's very important to choose a good learning rate, because if we choose a learning rate that is too small, the steps will be too small and it will take forever to reach this cost minimum. If the learning rate is too large, it will maybe happen that we overshoot. So we go here, then we go here, and then we go here. Depends on the learning rate, how large it is and how noisy the updates are. So it's also not great if we choose learning rates that are too large. So an advantage of using a stochastic gradient descent in deep learning compared to a normal batch gradient descent is not only that it is faster, but also it can help us to escape local minima. So in deep learning, usually we have these highly non-convex loss surfaces. So if this is my loss with respect to only looking at only one weight, it's usually much more complicated than that case here, where we have a convex loss function. So in this case, depending on where we start, we may not reach the global minimum. So imagine this is here the global minimum. If we start here, we go down this hill, then maybe we'll get stuck here, because then the gradient is not is 0 at this plateau, and then we can't update anymore. Sometimes it can help though to have some noise, because just due to the random noise, you will have an update here, although there's no gradient, and then you will jump out of these local minima, and then you have an opportunity to maybe at least go to this point here, which is not exactly the global minimum, let's say, but it is a good local minimum. So another advantage is the convergence speed. So stochastic gradient descent converges faster than gradient descent, and especially mini-batch gradient descent is much faster than either of the two. A mini-batch gradient descent is faster than the regular stochastic gradient descent, the online one with only one training example. And it is also faster than batch gradient descent. And why that is, we discussed this early in the introduction, or maybe lecture 4. So that is maybe a question for you. Do you know why mini-batch gradient descent is much faster than stochastic gradient descent? Because there were these two opportunities. I'm just seeing I have a typo here. This should be 2. Because of 2 opportunities for parallelism. So this makes it faster compared to online learning. So we can parallelize 2 things, and this is a question for you to answer. I don't want to answer all the questions for you. And also, like I said in the beginning, second order methods may even be better for minimizing a convex loss function, such as this one. However, like I said, in deep learning we have this highly non-convex loss surfaces, and in these cases second order methods usually don't work so well. So in that way, first order methods are still preferred. So I found a nice website that visualizes different optimization algorithms. So I'm not exactly sure how these are created. So because it should be actually a little bit noisier for stochastic gradient descent, but probably depends on how complex the loss function is in that case. In any way, so what we can see here at the top, I used the SGD setting here with a relatively large or high learning rate. What you can see is so the point where we start on this loss surface is this one here, and using the big learning rate, it's overshooting. So here again in the center is the global minimum, and then it oscillates, so it goes back and forth many times to find the global minimum, which is not ideal. The other case here is I'm using a small learning rate. So this is actually better. So in this case, it's not overshooting, but it's kind of impossible to see how many steps there are, but it would take more steps to reach the global minimum here. So in both cases, I mean, it's kind of tricky to find a good learning rate that is not too slow and that is also not overshooting. So it requires some tuning. And what are good mini batch sizes? So like I said in the last lecture, usually we choose them in powers of 2, like 32, 64, 128, 256, 512, 1024. And the common recommendation is that people are advised to choose a batch size that is as large as the GPU memory allows. So again, remember in deep learning, especially if you have fully connected layers, like with multi-layer perceptrons, you have a large matrix multiplication. So for example, if we have our weight, so the weight has the rows are the, no, I'm not writing rows here, the number of hidden units, and the columns are the number of features in the data set. And then our X, our data matrix, is number of features, and this is the number of examples, so which is the mini batch size. And this matrix multiplication, for this one we would, for example, write WX transpose, or we can also write, let me see, number of features, X transpose T, doesn't really matter. So we can write it either or. And this is a big matrix multiplication. It depends essentially on the number of examples. So reducing the number of examples will make the X matrix smaller. It will be a smaller multiplication here. And that will usually save GPU memory. So sometimes it's beneficial to just choose a mini batch size that fits into GPU. But again, we want to choose it as large as possible because usually it helps us with learning faster due to the two opportunities for parallelism, like I said before. One more thing to say about this here is I included this figure. I just wanted to also say, you remember this figure from the model evaluation part, but what I wanted to say here is also the smaller the batch size, the more skewed your label distribution will be. So it may happen that the label distribution in each sample will be noisier, or even just the samples will be noisier, and then you will have more oscillation again. But again, there are also papers showing that it is actually beneficial to have a small batch size because the noise can help with escaping these local minima. So like I said before, if you have this loss surface and you get, let's say, stuck here, there's no gradient here at this point. If you look only at the whole training set, it may be, though, if you have a mini batch that is extremely noisy, that the network will jump out of this, for example. So sometimes it's actually not too bad to have a small mini batch size. Yeah, so like I said, the mini batch loss is just an approximation of the training set loss. So the mini batch loss, if you plot it over for each iteration, for example, or for each over the course of the epochs, you will find it is oscillating. So, because like I said also before, each mini batch is just a random sample drawn from the training set. So it's not fully representing the data set or training set, it's just a small approximation of it. And approximations are usually noisy. So what I've drawn here is in blue the mini batch loss. This is for each iteration. And you can see the overall trend. So I'm also adding the exponentially weighted average here. Or you can also think of it as the loss on the whole training set. So if you would take the whole training set and compute the loss on the training set, you would get maybe something like this line. For the mini batch loss, you will, because it's an approximation, you will see it's more like oscillating. This is maybe not too bad because, like I said, this random noise can help jump out of local minima. However, it may be a little bit problematic when we want to really anneal the algorithm, that we want to stop it, that we want it to converge. We don't want it to jump out of local minima sometimes. Sometimes we want it just to anneal to a certain point, so there's no fluctuation anymore. And then, for example, the oscillation in the end may be a little bit annoying, so we maybe want to get something that converges more like this. So dampening the oscillation. And that can be achieved by just decaying the learning rate. That means making or shrinking the learning rate during training. So the longer we train, the smaller we make the learning rate. So there's one danger of using a decaying learning rate, and that is it may happen that we decay the learning rate too early and then we don't learn so well anymore. So what can happen is, for example, that we have a lot of oscillation, then we decrease the learning rate, but we decrease it too early, and then the network doesn't learn anymore, and the performance will be worse than using no learning rate decay. So personally, what I would recommend is just train the model without the learning rate decay, and then see whether you even need it, because sometimes the oscillation at the end is already very small. There are also different algorithms. We'll talk about some of them that don't have such huge oscillations, so maybe you don't even need it. And after you trained your model, you can just add it later. So I would recommend training the model without learning rate decay and then adding learning rate decay and see if it makes things better. Because like I said, the danger is if you just add learning rate decay from the start, you maybe decrease the learning rate too much, too fast, and then you don't get a good model out of it. So you can, for example, look at the validation performance to see whether with or without learning rate decay, things get better. Okay, now I want to show you some types of learning rate decay. So there are multiple types. I will only show you a small number of the most common ones. So one I would say that is most common is the exponential learning rate decay. All of them are pretty simple to be honest. So this one is just decaying the learning rate exponentially. So how that works is we have our learning rate at time t, and we multiply it by by a learning rate times e to the power of minus k times t. So where this is our initial learning rate. Okay, so this is pretty straightforward. I, on the right side, added a plot to illustrate this. I just see that this is not well ordered, so this is actually the smallest one. Would be nice if this would be on top. But doesn't matter now. Let's just focus on what I've plotted here. So in green, so this one, I'm showing you the highest decay rate, and this is on the x-axis the number of iterations. Could be usually the number of epochs. So usually we decay the learning rate each epoch, but you can also just do it more often if you like. Sometimes also people not decay every epoch, but maybe every 10th epoch or every 100th epoch and so forth. Really depends. And this is why using a decay rate is a little bit tricky, because it's hard to tell how much decay you need. So using a decay rate of 0.1, we get this green one. So it flattens pretty early at around, I would say, 50. It's pretty flat at that point. Using a smaller decay rate, 0.5, this is the blue one, it decays a little bit slower. And then the smallest one in this plot is the orange one, so that decays the least. But again, these are just some examples so that you get an idea. We start with a learning rate of 0.5 and then it decays it will converge to 0 basically. Another very straightforward way to decay the learning rate is just halving it. So again, you use the same approach, except now you halve the learning rate. So maybe this is not ideal how I've written this. Let's just call this t minus 1, not t equals 1. So every time point, so to compute the current learning rate, we divide the previous learning rate by half. So that's pretty straightforward. And then what we also have is the inverse decay. So this is the one I'm plotting here. So here I'm just dividing the initial learning rate by 1 plus k times t, where again k is the decay rate and t is the iteration. Which one you use doesn't really matter. I think all of them serve the same purpose, shrinking the learning rate over time. And like I said, it's kind of tricky to find good values for that. So it needs some experimentation. It was an interesting paper I've seen that was 2 years ago by Leslie and Smith. So in this paper, the author did some experiments with a cyclical learning rate, which is, it looks maybe a little bit strange, but it seems to work well in the paper at least. So what the author did is, for the learning rate, just cycling it between a maximum and a base learning rate, just going back and forth, increasing, decreasing, increasing, decreasing. Maybe the reason why it works could be, for example, sometimes you want some noise to escape local minima, but then you want to not jump out of other regions, so you in that way anneal and then jump out of local minima and anneal again and so forth. Maybe that's why it helps. I have no idea, to be honest. Personally, I tried this on some of my projects. In my case, unfortunately, it did not do better, but I heard from some people that it helps, so it's maybe also something interesting. How can we apply learning rate decay in PyTorch? So we can, option 1, just write our own function. So for instance, I'm showing you a function that I wrote that would update the learning rate every 10th epoch. So in this function, we give it an optimizer, the epoch index, an initial learning rate, and a decay rate. So this will implement the exponential decay. So how this works is I'm just multiplying my initial learning rate by this exponential term, and then I'm updating the learning rate inside the optimizer. So I'm applying this parameter groups loop here. So in case there are multiple parameter groups in the optimizer, it will update the learning rate for all of them. It is usually not the case that you have multiple parameter groups, but it's just more general to do it this way. So there are also multiple versions of learning rate schedulers in PyTorch. So these are a little bit more, I would say, sophisticated than the function that I just showed you. So for example, here I'm showing you a lambda learning rate scheduler, which accepts 2 arguments. So one is when we want to update. So how many, so which epoch we want to update. For example, every 30th epoch here. And also how we want to update. This is a second lambda term. And then we just provide it to this optimizer. And then during the training, what we do is we call this step method of the scheduler, and this will update the learning rate. So this would be typical training loop. So train would perform then the model training and validation, some validation of the model on the validation set. But this is something that is what you would write, and this is a scheduler step what you want to do just for optimizing, or not optimizing, but for decaying the learning rate. So here's another example doing exactly that for the exponential learning rate decay. So here I'm using one of the inbuilt learning rate schedulers in PyTorch, and I'm using the stochastic gradient descent that we used previously, the SGD optimizer, with an initial learning rate of 0.1. So what I'm doing here is I'm simply initializing the optimizer, and I'm initializing my scheduler, which depends on the optimizer, right? So this is, the optimizer contains the learning rate that we want to update. Then we choose our gamma, which is our decay rate k. And also I give it the index of the epoch. So here I'm just saying last epoch. Next, so here, this is the training loop, how the training loop actually looks like. So in the previous slide, I initialized everything and now I'm training it. So like always, I would load my data, transfer it to the GPU if I have a GPU, and then do the forward pass, compute the loss and set the gradients to 0, perform backpropagation, and here I'm just logging the results if I want to plot them later. And here I'm applying my scheduler.step. And again, I don't have to do that every epoch. I can skip epochs if I like, for example. So for example, I can do if not epoch, let's say 30, and then I indent this by 4 spaces, then it would only perform this update every 30 epochs. One last note about the coding part. Also, when you want to save your model in PyTorch, you want to save the state of the scheduler, because the scheduler keeps track of the epochs, and to get the updates right, you also want to save the state. So in this case, there are not many parameters. There's only the epoch parameter. So we want to keep track of the epochs. That would be our t. So t is always, so it is, when we call a step, it's counting the epochs. So t would be the count of the epochs. We want to keep track of it when we save our model in case we want to train our model further. So in order to do that, it's the same approach that we use for saving the model itself. For example, what I usually do is I transfer the model to the CPU first before I save it. It's not necessary, because when you load the model, there's an option that you can load it onto the CPU. It can be a little bit problematic though if you don't transfer the model to the CPU and then you forget to add, I think the parameter is called device. If you forget to add the device CPU here and you want to load it into your main device, then you may get an error, because here it thinks the parameters are on the GPU if you don't call this device.cpu, and then it gets confused. You just have to make sure that you use the same device for saving that you use for loading, but usually this is not an issue. Just so I don't forget, or no one, because some people don't know about this device, so some people, when I send them a model, they don't know how to load it, so I usually export the model to the CPU first. So what I'm doing here is I'm saving the model itself. So I'm saving a state dictionary of the model. Then I'm saving the optimizer state. So that is also helpful. Stochastic gradient descent, it does not matter, but there are some other algorithms we will talk about shortly where it does matter, where we want to also keep track of the state. And then here I'm saving the state of the learning rate scheduler. So I'm saving 3 things here. And then let's assume I want to continue training. I have to load all of them, but it's actually pretty straightforward. If we want to load something, we first define it, the model, and then load the parameters from the state dictionary. And we do the same thing for the optimizer. So we initialize our optimizer, load the static. In this case, it's not necessary because there's nothing really fancy going on in the stochastic gradient descent, but for momentum learning, which we will talk about shortly, it will matter. And then we also here load the learning rate scheduler. So using torch load and then these PT files. So the PT files are, you can think of them as Python dictionaries that save the model state. So just a few last words about the learning rate and the batch size. So there was recently this interesting paper. I mean, not that recently, it's 2017, but I was just recently remembering it. So here the authors looked into the relationship between learning rate and batch size, and they give the advice, so instead of, so they say it's common practice to decay the learning rate, but they advise, for example, instead of decaying the learning rate, increasing the batch size. So with increasing the batch size, you can get similar good properties as with learning rate decay. So here are two plots from that paper using an inception and ResNet architecture. We'll talk about inception and ResNet later in the convolutional neural network lecture. So here what we can see is the validation accuracy for the number of epochs stays or is about the same for all the different methods. So they have two learning rate decay methods and two increasing the batch size approaches. So they have just different settings for those, and they compare the validation accuracy. It's almost the same, I would say, for the red one and the blue one. They are almost identical. The red one is increasing batch size, and the purple one is, or blue one, is decaying the learning rate. However, what is interesting here is on the right side, what you can see is, so here, what you can see is that, so here they are plotting the number of parameter updates. You need fewer parameter updates for reaching this performance. So for increasing the batch size, these two, you can see after about, I would say, 5,500 parameter updates, you already achieve the performance here. And for the learning rate decay, you need much more, or many more updates, more than twice as many updates. So in that way, just increasing the batch size may already be doing what you want. So maybe you don't need learning rate decay to get good performance. And also it's faster. Okay, next we will talk about momentum. So momentum is the first trick we can apply to help SGD to learn better, and that is by dampening the oscillations. So the term momentum is probably inspired by physics or Newtonian mechanics, where the momentum is the product between mass and velocity. So in deep learning, I mean, we use a lot of jargon terms, and we borrow a lot of terms from different fields and make them mean something different. So here we will talk about momentum that is maybe inspired by this term, but it's not the same. So here we are only focusing on the velocity term. But again, the focus here really is to accelerate the convergence so that SGD may converge faster and to reduce the oscillations. So with reducing the oscillations, what I mean is, so I was drawing here two loss surfaces, and sorry if I'm going a little bit fast now, but I'm just looking at the clock and I want to keep the lecture short because some students complained it was too long last time, so I want to keep it to the regular time. So I'm going maybe a little bit skipping the trivial parts. So here on the left we have optimization without momentum, so it's usually a little bit oscillating as we have seen before. And if we add this momentum term, the velocity, we will dampen it a little bit. So it will be, if the velocity is in this direction, for example, then we will have this gradient direction plus the velocity, and together we will have more something like this, where we oscillate less and make more progress into the right or straight direction. Okay, so the key takeaway is that we not only move in the direction of the negative gradient, but we also move in the average direction from the last few updates. So we kind of keep a memory of the last updates and move into that direction. So this helps with the oscillation aspect. So we dampen the oscillations with this velocity term or momentum term that we add. But at the same time, we can also avoid getting stuck in local minima, because we still have this momentum from previous updates that allows us, if we have a flat gradient region, to jump over these regions so that we don't get stuck there. So the equation looks more complicated than it really is. So all we do with momentum is we add a velocity term, which is this one. We add this term to the regular gradient term that we usually compute in stochastic gradient descent. So usually we compute the partial derivative of the loss with respect to the weight that we want to update at a, let's say, time point t. We multiply it by a learning rate. And in addition to that, now we add this momentum term, which is an alpha, which is the momentum rate, which is some number between 0.9 and 0.999 usually. It can be smaller, it can be bigger, but usually that is a number that works well in practice. So the larger this number, the stronger the momentum term. And we just add this whole thing to our partial derivative times the learning rate. And or in practice, we call it usually the velocity term. And then we use the velocity, which is the previous velocity, time point t-1 plus the gradient update, to update the weights. So this is just the regular weight update that we perform. So usually in practice what we do is we subtract the negative gradient, so then that term. But now in addition we have this whole term, which is the momentum term plus the negative gradient. Or in this case it's not the negative gradient, which is why we subtract. Okay. So here's an illustration of how that looks like in practice. So I'm using momentum term. Actually they call the momentum term 0.99, but yeah, I just called it alpha in the previous slide. And here the alpha is actually what we call eta, the learning rate. But this is just a minor detail. So what I'm trying to show you is with zero momentum. So this would be alpha 0 in our previous slide, which would mean that we cancel this whole term here. We have a large oscillation. This is just regular stochastic gradient descent. And then it gets maybe even stuck here. Maybe it doesn't even find the optimum because the learning rate also is relatively small, and it converges here to here's maybe a flat region, so there's no gradient anymore, so it doesn't reach this optimum. If I add my momentum term now, I have some velocity from the previous updates. So with that velocity term, it goes a little bit zigzag like before, but it doesn't oscillate so much because it has this velocity that drives it in this direction. And you can see it doesn't get stuck here. It goes, thanks to the velocity, over this point here and gains again some gradient to find a solution which is very close to the optimum. So how can we do momentum training in PyTorch? That is actually super simple, so we don't have to do anything fancy. We can just use the regular SGD optimizer, and we can set the momentum rate here. By default it's 0, so that means there is no momentum, but we can then just set it to a number, let's say between 0.9 and 0.999. You can also use, like I said, a bigger or smaller number, but these are usually numbers that work very well. You may also see there are additional terms. So there is a term dampening, and there is this is maybe the most interesting part because it says dampening for momentum. So how is that related to momentum? Yeah, since we are short on time, I don't want to spend too much time on the dampening term, which is not super interesting anyways. So the dampening term is an optional term for momentum learning, and this is simply scaling the gradient component of this velocity. So in that way it's not super important or super interesting to use that one. You may use that one, it can help in practice. So if you, for example, choose a value smaller than 1, then this value will be larger than 1, and then this gradient term will be larger compared, for example, to the second term. So this is just another parameter to control how much influence each of the terms has. So so it was also mentioned here, another interesting modification of the momentum method is the Nesterov accelerated gradient, which was it's just based on a method by Yuri Nesterov it was written up in 1983, and then adopted for stochastic gradient descent in deep learning by Sutskever, Martins, Dahl and Hinton in 2013. And this is a small modification to momentum that applies this correction term here. So the gradient incorporates the term that we also use as the momentum update term. So when we compute the velocity term, we use the previous velocity, this term, multiplied by the momentum, so this term here. And notice that this is actually subtracted from Wt. So here what we do is we perform an update and then we subtract in the way based on the gradient, based on where the method would have ended up with a regular update. So this is maybe a little bit complicated to conceptualize, so I posted the illustration from the paper, so from the Sutzkever paper. So at the top they have the regular update, regular momentum. So this is just the direction of the gradient, and this is the momentum term. So it's the previous velocity times the momentum coefficient. So together this is simply this term. And we add them together, so we end up with this new velocity term here. And this is also by how much we update the gradients. So in the modified version, what we do is we have still the momentum term, but then, so this is again still this term, but then we correct this term using, by subtracting this term. So here this is a plus, but it's just the way they've written the equations. This is equivalent to this minus term here. So we correct the direction, so this is now pointing down. So this is maybe useful if we want to do the update in a more smarter way, because the gradient here in the top is computed without knowing. So we don't know this velocity, so when we compute this gradient here, this one doesn't know about this velocity here. So this is maybe not a good gradient if it's done in the absence of the velocity. So here we have this correction term to correct for the velocity also. Okay, so that was about anything I wanted to say about momentum. Like I said, I don't want to take too much of your time, so let's go to adaptive learning rates. So adaptive learning rates are based on the concept that we adapt to the current situation. For example, if the gradient changes the direction, we decrease the learning rate, and if the gradient stays consistent, we can increase it. For example, if we have an update, let's say like this, where it's going in the right direction, we can also increase the learning rate every time because we know we go into the right direction. But let's say we have something crazy where we have an update like this and then like this, that is going in the wrong direction, so it changed the direction maybe because we have a noisy sample. We want to decrease the learning rate because we don't want to make a large step in the wrong direction basically. So just to set up the scene how that might look like in a very simple scenario, so the simplest way we can adapt the learning rate, that would be, for example, just by using a gain parameter. So this gain parameter is for each weight, and we can then monitor during training the weights whether they change the direction or not based on the gradient. So we would have, usually we compute the loss with derivative to each weight. We use usually linear algebra, but we can still look at the gradients for each weight. And then we say if the gradient is consistent, we add a term here, a term beta. So I will show you in a moment what beta is, but I can just tell you, for example, that this is a number, say 0.99. So we add a number if the gradient is consistent, so we make larger step into this direction every time. So we increase the gain. And the gain, again, this is not added to the gradient itself, it's multiplied by the gradient. So if this is a positive number, it will increase the gradient at some by some value. But if the gradient is, this is when the gradient is consistent. If it's not consistent, we do this update. So here we multiply the gain. So t minus 1 means the previous step, the previous iteration, and t is the current one. So here what we do if we are inconsistent, we multiply by 1 minus beta. This has a dampening effect, and multiplying this gain by a number has more effect if gain is large. So here we always add a constant. Here we multiply, which has a larger effect if the gains are already large. So this is kind of important, because if we make steps in the right direction for a long time, we can just increase it because we are sure we make steps in the right direction. But if we suddenly change the direction like this, we don't want to make a huge update. If we already accumulated a large gain, for example, we don't want to make a huge update if it's a different new direction. We might maybe want to adapt to the new direction slowly. So here the gain will be having a bigger impact if it's already large, because we multiply by this factor here. One popular method where an adaptive learning rate is used is the RMSProp algorithm by Geoff Hinton. As far as I know, this is an unpublished algorithm, and Geoff Hinton talked about it in a Coursera class that he taught. Unfortunately, the class is not online anymore. Anyways, so this RMSProp is based on RProp, which is by Christian Igel and Michael Hösken, and it's conceptually very similar to another concept called Ada Delta as well. So we are not going to cover Ada Delta, but just to give you the brief idea. So what we do is we divide the learning rate by an exponentially decreasing moving average of the squared gradients. Sounds like a lot. It actually looks simpler than it really is. And the purpose of this is it takes into account that the gradients can vary when they have a large magnitude. They can vary more. So gradients that are large, they can fluctuate more than small gradients. So the idea is to also take that into account. And the reason why it's called RMSProp is because it uses the mean squared term here for decreasing the moving average, basically. So similar to momentum, this has a dampening effect as well, but in practice it works a little bit better. RMSProp is really simpler than it looks like. So there are only two things going on. One thing is that we modify the gradient update. So this is the regular stochastic gradient descent update. And now what we do is in addition to performing the regular update, we scale the gradient term here. So we use a term that is the mean square term, and we have a root here. So the root mean square prop algorithm. So here we have a square root and the mean square. We'll show you in a moment how the mean square is computed. For a second, also look at this epsilon term here. This is just added to avoid a division by zero error. So the mean square term here, this term is computed. So it's replaced every epoch by itself, basically by the last iteration. So this is time step t minus 1. So at the current time step, this mean square term gets updated by this whole thing and becomes the new mean square term. And why it's called mean square is simply because we have a squared weight gradient here. We square the gradient of the loss with respect to the weight here. And that is all there is to it. So we have these betas, which are usually numbers between 0.9 and 0.999. And these are then also like the dampening terms. So with that we can influence the dampening. So the whole thing is similar to a moving average, except that we have the square term here. Okay, so the last algorithm for today is Adam. And Adam is, you can think of it as a combination between momentum and the RMSProp, which is more as like an adaptive learning rate. So with Adam, so the most, maybe the easy way to explain this is by combining what we have seen before. But let me just simplify it a little bit. So here, this is the original velocity that we computed in momentum. So I call it the momentum-like term. So here what I'm simply doing is I'm replacing this part by just mt minus 1, so m for momentum, so easier to memorize. And then I'm also replacing this by mt for the current time step. And I'm getting rid of n here. So I will, instead of n, I will use 1 minus alpha here. So I'm writing a term that is not exactly like momentum, but very similar. So except for the learning rate, I have now 1 minus alpha, where alpha is this one here. Alpha was our momentum coefficient. So it's very similar to the original momentum, a little bit different. So the reason why I'm doing that will be clear in a second. So in the center here, I have my RMSProp term. This is what I just introduced 2 slides ago. I'm just calling it R here, just for short. And in Adam now, so each weight in Adam will be updated using both a momentum component and an RMSProp component. And this is also why it's called adaptive moment estimation. So the adaptive part from the RMSProp idea, and then the moment part from momentum learning. So how this works is simply when we perform the weight update, we have the momentum-like term at the top, where we have an alpha and 1 minus alpha here. Again, this is similar to momentum, but not exactly the same, because in the momentum we also had the learning rate here, but doesn't matter for now. So we have this momentum-like term, and in the denominator we have the R term here from RMSProp. This is very similar to what we've seen in the previous slide. So in the previous slide, 2 slides ago, we also had square root of the mean square term here for scaling the learning rate, the gradient. Here we use same thing. And yeah, this is Adam. It's just combining momentum and RMSProp, and it works super well in practice. So here is some more detail. This is the whole algorithm from the paper. So the paper is from 2014. 2014 is old in terms of deep learning because the field is moving super fast. However, this is still a very commonly used algorithm, very popular algorithm, and most of the time, most of the people still use it because it works great. There's just one little modification that I didn't have in the slides. So there's a bias correcting term here for the first moment estimate and the second raw moment estimate. So here beta, this is for our momentum-like term, and here the beta is similar to beta 1 is similar to what I've written here as alpha, and beta 2, what you see here as beta 2 is simply what I have as beta here. I find it easier to have alpha and beta. It's easier to distinguishing the two. Here they just call it beta 1 and beta 2, but it's the same thing. Okay, so in PyTorch there's also, of course, an Adam optimizer, and I recommend from now on using that one instead of SGD because it's easier to get this to work well. You have to spend less time with learning rate tuning. And yeah, also they have a parameter, the betas here. So for the first beta, usually people choose a 0.9, and for the second beta, it's a 0.99. So in our case, this was the alpha. Oops. Yeah, so there's not much more to say about this. So this is the one that we can use now instead of SGD. Here's a nice article that has a visualization. So here all the algorithms start at this point. And for example, for SGD, it goes like this. Oops, it's a black line. And momentum goes like this. It has like this huge velocity build up, and then it overshoots a little bit and then goes to the center. RMSProp does something a little bit weird, but also finds the center. And Atom is a little bit even more extreme because it now has the momentum term, so it goes more to the right. And then comes back here. The reason why I'm showing you that is that in practice Atom works often much better, but it's not always true, and this is also maybe a bad example because it's a very simple loss surface, and here in this case maybe it's not great to use a sophisticated algorithm. Using stochastic gradients may be sometimes just fine. However, it really depends. Sometimes one algorithm is better than the other. In this case, they are all quite fine. Okay, how do we use that in PyTorch? So this is a very, very short section. I know I'm running out of time here. So how do we do optimization using these algorithms in PyTorch? You have already seen the SGD optimizer. So the SGD optimizer is what we have used before all the time. If we want to do momentum learning, we can just add this momentum parameter value here. That's about it. That will give us momentum. And for Atom, we can use this Atom algorithm here. So instead of using SGD, we will just use Atom. And like I've shown you here, there's the beta parameters that you can change, but usually people don't change them. Usually you can keep the defaults and it will work quite well. Okay, one more note is to save the optimizer state if you are using momentum or Atom, because now we have some parameters that are updated over the epochs. For example, the velocity or momentum term that will build up. So it's also important to save the state of these if you save the model. I've shown you that in the earlier slides. One last note about SGD versus Atom. Like I said, I recommend really using Atom. However, if you have a lot of time and do a lot of tweaking, usually SGD will give you better results, but it requires a lot of tuning, often also weight decay, and it's kind of tricky. But if you really want to get the best performance and you have a lot of time, then SGD may actually be better. So there was a paper 2017 comparing the different algorithms. So on the left, this is the Atom paper, and Atom here is the one, so they show the training cost, the lower is better. Atom is the one that gets the best performance here compared to other methods. For example, RMSProp, SGD with Nesterov, ADA delta, and ADA grad. So, but if we look at just the regular SGD, this is done here on the right side. What we see here is SGD oscillates more. This is something we already suspected because we don't have this dampening term, we don't have momentum and velocity, stuff like that. So we have more of this random noise oscillation. However, you will see that eventually it will find a lower or a better local minimum. It will result in a lower test error. The reason is why people think that is noise can be good, because if you maybe fit or loss surface the loss too closely, if you optimize too well, you maybe find a local minimum that is really good in terms of minimizing the loss. However, it's maybe overfitting, so the generalization performance will not be so good. So that is why you sometimes observe that regular SGD will give you a better generalization performance than Atom, for example. Okay, I hope I'm staying on time here, so because there were some complaints, the lecture was a little bit too long last time, so I want to keep the 1 hour and 15 minutes official lecture time. There's just a short reading, it's actually a long reading, but you don't have to read all of it, but it's a good overview of the different optimization algorithms in deep learning by another Sebastian. It's not me, but it's a great article, so I really recommend this one. And yeah, that's about it. So in the next couple of slides, I will briefly talk about stuff in the news, but if you have to go now, we should be at the 1 in 15 minutes. So then, yeah, see you on Thursday. So let's talk about some of the cool things that happened in the machine learning and deep learning world last week. So just today I saw this nice, interesting, cool library called Torch Layers. So this is not an official PyTorch library. So you always have to be a little bit careful because they may not be maintained forever. So sometimes people stop making them or updating them. So this was a library by a PyTorch user, but still a very nice and cool project. So here, this library simplifies how you can set up your PyTorch model. So you can just use sequential without any other additional steps. And also what's interesting is it's doing some auto-guessing of the input dimensions. For example, here for the linear one, you only have to specify the number of outputs. You don't have to specify the number of inputs. So it's automatically guessing. So here at the bottom, they basically illustrate with a question mark what the network is guessing. Yeah, so there are also convolutional layers. And convolutional layers is something we'll talk about on Thursday. So in 2 days. I hope you are excited. Okay, so that was one nice thing. What also was super cool, this is not super new, but it was recently shared in the news, is this anime GAN. So it's already a year old, so it doesn't technically count as stuff that happened last week. But anyways, it's so cool that I wanted to share it with you. So what they did here is they trained GAN and combined it with neural style transfer. So this is the original photo, and here this is their anime GAN. And what they try to do is to make a photo look more like an anime that people would draw from the photo in a certain style, in the Japanese anime style. So what it does, it's combining neural style transfer and generative adversarial networks. And GANs are also a topic, or again, the generative adversarial networks. So this is something we will talk about also in a later lecture in this course. And they are models for generating new content or data. For example, here they are making a photo looking more like an anime, which I think looks super cool. Especially I liked this picture here, which is taking this photograph and converting it into some anime. And I would say this really looks like something someone would draw in an anime, in what you would see as a video, for example. I think this looks super cool. Yeah, another thing that happened this week as a response to the increased usage or the increased use of technology for telecommuting. So for example, conference calling software like Microsoft Teams. So I think Teams is currently Microsoft's most popular conference call tool. I usually use other tools, but I heard for many this is a pretty cool tool, and they just added a new feature to it based on deep learning. So in another article that was described as a neural network that is doing that. And what they're doing is they're applying deep learning to remove background noise that is annoying in a call. For example, a leaf blower, a barking dog, or even if you eat a bag of chips during the call, it may be able to filter all the noise, but I wouldn't rely on that. So maybe don't eat bags of potato chips during a conference call. But yeah, that might be something that is not too bad. That's actually a pretty cool idea. There were some students asking questions about what is a good model size and what is a good size of a data set for deep learning. It's hard to answer. I mean, what is the expected performance for a certain type of network? Always depends on the data set. However, there was recently a really cool research project that designed an equation or cross-entropy or loss landscape that can relate the model size and the data set size with the expected generalization performance. So here they try to model the data size and the model size and the data size in relation to the error. So here they have the log 10 of the error, the log 2 of the data set size, and the log 2 of the model size. And I think with model size they were only looking at the width of the network, and I'm not sure about the depth, but doesn't matter. Also the depth, okay, both. So that was actually pretty cool. So with that, looking at the depth and width, they could come up with an equation that can capture the relationship between the error, the data set size, and the model size pretty well here, as shown in these two figures, which is, I think, also nice, cool research.